Oh my god, jag skulle ju... Okay, good morning. So today we talk about this lesson. It's more theoretical, but it is needed. So I want you to know about this topic. Hopefully I can cover it in one session. Okay. You are familiar with the notion of limits?
Yes.
So what is a limit? Yeah, the limit is a little bit hard concept in mathematics, but intuitively it's very clear. So when you write the limit of a function f of x, when x approaches a is equal to L, what do we mean? It means that if it means that the values of the function can be close to this number L as desired, but the condition is that I have to be sufficiently close to this value A. When I say the limit of f of x, for example, when I say the limit of 2x when x goes to 5 is 10, what do I mean? I mean that the values of this function becomes very close to this value when x values are close to 5. Yes, that's the mean. Okay. You already know about the concept of limits. So this symbol in mathematics, when we use that, what does it mean? It means that x is very, of course, very should be in quotation mark, because if I want to make these terms precise, it would be beyond the scope of this lesson. So, but you understand, x is very close to A, but this is important, but x is not equal to A. This is crucial. So it means that we don't care about the value of the function at that point when we talk about the limit of the function when x approaches to that point. So it might be the case that the value of the function is even not defined at that point, but it doesn't mean that I cannot talk about the limit of the function close to that point. And that was exactly the reason that the notion of limits actually came into mathematics. So it means that we want to talk about the behavior of my function, not exactly at one single point, but in the vicinity of that point. Yes? Okay, so this is I want you to understand. Okay, and today actually we want to use the idea of limit to understand what is the connection between the concept of a limit of a function and the continuity of the function. So because we have an intuitive understanding of continuity, yes? So it means that, for example, if I ask you, so just let me rely on your intuition. I draw a graph for you here, y equals to f of x, and I actually pick a point on the graph, for example, this point, and then I tell you that, okay, assume that this corresponds to A, here. Now I ask you this question, do you think that this graph, just rely on your intuition, is continuous at this point or not?
Yes.
Yes, because you see that continuity means I can draw the graph with just one pen stroke without lifting the pen from this whiteboard. So you see that there is no breaks or something happening exactly at this point. So you feel that the function should be continuous at that point. This is our intuitive idea. So it is a very elementary task. If I draw a graph for you and ask you if the function is continuous or not, in a matter of seconds, by looking at the graph, you say that yes or no. Yes. For example, if I give you this type of graph, for example, I can just give you this, I would say that this is another graph. Do you think this graph is continuous? So it is not. So I mean, this is easy task. But the point is the opposite. The point is that I do not have access to the graph of the function. I have access to the formula for the function. And I want to know that if the graph of the function is continuous or not. or if it is not continuous, at which points this discontinuity can happen. Is that clear? And I want to make it so sensitive that even if this breaking happens at one single point, I should be able to detect that. So for example, if I draw such a graph, for example, it comes from here up to here, and then assume that exactly, of course, even on computer, it is not possible probably to draw one single, because one pixel out, you cannot feel it. But this is the way we use to say that, okay, this is a function. But do you think this means that consider the whole curve, exactly one point of it is singled out? It is not possible to draw it because for a point we do not have any dimensions. So if I just take it out, you cannot see it, yes? But this is the way that in mathematics, if I want to convey this message, I would say that this function is not defined at that point. So you see that I cannot draw it with one pen stroke, because in principle I can come up to here, then momentarily I have to lift my pen and put it a little bit there and then continue. A little bit there, it doesn't make sense because there is no dimensions. Okay, so still I want to understand this behavior. I mean, if I have a function which is even discontinuous at one single point, I want to be able to detect it before seeing the graph of the function. So that's my point. So we want to understand the connection between the concept of limit and the concept of the continuity of the function. Yes? Is that clear? So what's the idea? Okay. So there are some kind of conventions here. Let me talk about these. So you see in the book, sometimes on a diagram you have a hollow circle, and then sometimes you have a filled dot. So they put it there intentionally to convey some message to you, okay? It's not just for the decoration, okay? So let me just talk a little bit about this convention, graphical convention here. So let me just draw a function for you like this. By the way, don't say that I have two functions. The whole black curve is the graph of one single function, yes? Okay, so here the same thing. So assume that I come up to here, and then I put a hollow circle here, and then I go higher a little bit, and then I put a filled circle, and then I continue like that. And then I would say that assume that when I go down there, this is A. If I go horizontally, assume that this is given to be L. If I go horizontally from here, assume that this is M. Okay, let me ask you this question. Assume that the whole black things that you see here on this diagram, except the coordinate axis, of course, is the graph of one single function y equals to f of x. Okay, if I ask you what is f of a, what is the answer? So if I give you this, and I say that, okay, this is a, this is y equals to f of x. If I ask you what is f of a, this is a very simple question. Yes, you go upward, and then when you find the intersection, you go horizontally. When you get a number L, you say that f of a is L. Yes? So what is f of a in this case? It is M. Yes, because that's the convention I want you to learn. If you go vertically, the intersection does not happen here, because that is hollow. It's dodging you actually somehow. Then you go up there and then intersect there. Okay, so the f of a value is M, not L. Okay, or for example, let me also make this hollow and then put the filled dot here and say that this is K. If then I ask you the same question, what's the answer?
K.
K, yes, because the intersection happens there. So this convention, in drawing the graphs, I want you to differentiate between what I say when I draw a hollow circle or a filled dot. What is the difference? So that's f of a. Yes? Okay, so that's one thing I want you to know. The second thing is we want to understand the limits from the left-hand side and the right-hand side. Let us see what is important here. Okay. So let me draw a graph for you here. And by the way, let me ask you one more question. If I completely clean this and ask you the same question, what's your answer? Undefined, because that's also important. So if you don't have anything there, and then you say that f of a is undefined, yes? It is not in the domain of my function at all. But that is also important. Even though f of a is not defined, still I can talk about this function, this limit. I cannot say that, okay, the function f is not defined at a, so let us completely forget about the limits of the function at a. Okay? They are somehow related, but for having this, you really don't need to have f of a defined. It might happen that this is not defined. Okay, let us try to understand now. So what I want to do now, I want to motivate you about a good definition of continuity. Okay, so I want to motivate what I will define shortly as the definition of continuity is plausible and reasonable. That's the motivation. Okay, so so let me just consider some cases. For example, let me consider this function with this graph. Okay, and then let me call this point A, and then let me this value to be L, and this function is y equals to f of x. Okay, and then let me jump a little bit higher and put the dot up there. Yes, and then give this a name M. Okay, again, forget about the axes. Every black thing that you see is the graph of one function. Yes? Okay, if I give you the graph, the black parts, this, that, and this dot, do you think my function is continuous at point A? No, it has broken there, yes? There is only one single point, but still, it is not continuous. Let us see how we can detect that. Okay, so I start calculating the limit when I approach A from the left and from the right. So, for example, let us be close to A. Assume that I am here, but I am on the left side. And then I want to get closer and closer to A and try to see what will happen to the values of my function. If I am here, this is the value of my function. If I get closer, the value becomes a little bit larger. If I get even more closer, this value becomes larger. Then the value becomes larger. Yes? And hopefully you understand what is happening. So when I get closer and closer to A, these lengths are actually getting closer and closer to which value? No, I'm just getting closer to this one. So this is the first height. When I get closer in this function, you see it is increasing, increasing, increasing. When I get closer and closer to A, but I do not stand exactly at A, what do you see for these blue lines? The length of these blue lines are approaching a number. What that number is? It's L. Yes? The length. It's getting closer to this length level. Yes? So if I want to show this behavior, I would say that the limit of f of x when x approaches A, and I put a minus sign on top, not because this is negative. This minus sign that I put on top, it shows me the direction from which I am getting closer to A. So you see that this value becomes L. Okay, now let me just do this the other way around. This time, I start from the right-hand side of A, say somewhere here, and then I get closer and closer to A, but I do not stand exactly at A. That is the important thing you remember, okay? So this is the value that I have when I am here. If I get closer in this function, these lengths are getting shorter and shorter, yes? Okay, be careful. I am not allowed to stand exactly at A. So what do you think this will happen? These lengths are also getting closer to which value? L itself. Yes, so this means that if I want to write this behavior, to represent this behavior symbolically, I write this one is also L. So the left limit and the right limit are equal. Okay? So this means that the conclusion out of it is that the limit itself is what? It doesn't matter in which direction I approach A. The value of the limit is L. But what is the value of the function at A? But what is f of A? It is not L, it is M. Yes? And that is the reason, by the way, that I have this breaking in this graph. Because the limit is at a number, but the value is a different number. The value of the function is M, the limit is L. These two values are not equal. That is an indication of discontinuity. Okay? So this means that limit of f of x goes to A, is not equal to f of A. So this implies that f is discontinuous at x equals to A. This is an observation, yes? So we realize that even if I have this scenario going on, then what is happening? This function is discontinuous at that. But let me give you another scenario. For example, the first diagram that I drew. So let me just try to do this. Or let me just do it a little bit differently. So I come here, and then I have a filled circle, and then I go a little bit lower, and then I have a hollow circle, and then, for example, I go back upwards. Okay? And then exactly at this point, if I give you the information, this is assumed to be A. If you want this, I can give you this height as well. So I call it M. If I give you this, yes, that is, I call it L. And again, the whole black thing that you see here is the graph of one single function, which again I call it f of x. Okay, so let us try to investigate again. First of all, if I ask you what is f of A, what is your answer?
L.
This is L in this case, yes? Okay, but now let me ask you, what is your opinion about the limit of the function f of x when x approaches A from the left side? So what happens? It means that I am somewhere on the left-hand side of A and close to it. So let us start from here. What is the height of the function if I am here? So the height of the function, I go vertically upward so that I intersect with the black curve. So that's the height. Then I go closer. So what happens? I go higher, higher, and then, okay, now the intersection is there. And then I go closer. I go even closer. But the point is that I am not allowed to stand at A, yes? Okay, so what is your guess about this limit?
L.
You see that these lines are getting shorter and shorter, but they cannot go below L, they get very close to L. So this limit is L. Okay, and let us try to investigate the other side. So x goes to A from the right-hand side. So then I am, for example, standing here at some point on the right-hand side of A and close to A. And then this is my height for the time being. And then I go closer. This line becomes shorter and shorter this time. So what is happening? These lengths are getting closer to which number?
M.
M. But you see that L and M are not equal. So what does it mean? It means that if I ask you this limit, what is your answer?
Discontinuous.
No, the limit does not exist. The consequence is that this is discontinuous. So the limit does not exist. Because depending on which side of A you are approaching to A, it is L or M, and L and M are not equal, so we cannot talk about the total limit. We can talk about the left side limit, We can talk about the right side limit without any ambiguity, but we cannot talk about the limit itself. Okay, so this means that one of them is equal to the value, but the other one is not. So in general, again, this limit does not exist. So you see that if I want to face discontinuity, I have two scenarios, yes? What is happening? There's another scenario. Let me also do that and then we can summarize it. So what happens if I have just this function? It comes here, there is a hollow circle, I don't know, it continues, for example. And then this one is A. Just hollow. Okay, so what do you think? The function is not discontinuous because I have a break in it. But if I ask you, and I give you this limit, I give you this number to be L. And if I ask you, what is your opinion about the limit of the function when x approaches A, from left or right? Do you think they are the same? If they are the same, of course, you can say that that's the same number. So what's your opinion about the limit of f of x when x approaches A? Yes? L. It doesn't matter on which side we are getting close to that, that's L. But now, if I ask you what is f of A, undefined. Okay, so you see that the continuity is closely related to this limit. If you want to know if the function is continuous, the things that matter is this limit and the value of f of A. These two matter, yeah? So in any way that they are not equal, the function is not continuous. Is not equal has different meanings. Sometimes this exists, but they are not equal. Sometimes this exists, but this is not defined. Or sometimes the limit does not exist. For any one of these cases, you are facing a discontinuity. So if you want to have continuous, what is the definition, a good definition of continuity? Can you tell me? So let me just write it down and I ask you, okay? So, definition. A function f is said to be continuous at x equals to A if, okay, can you fill up this gap now? Yes?
Maybe if the limit of f of x as x goes to A is equal to f of x.
Yes. That's the definition, yes? If the limit of f of x, x going to A, is f of A. If this is not going to be the case, okay, all possible scenarios, if this is not going to happen, either this might not be defined, so you have discontinuity, or might be this is defined, this is also defined or exists, but they are not equal. Then you have another scenario. Okay, all possible. So if this is not the case, you are having a problem from the continuity part. Of course, you can write this in this form. If you want to write it explicitly, you can say that 1, f of A is defined. Yeah, but this symbol is good to write. 2, limit of f of x, x goes to A, exists. 3, these values are the same. But you really don't need to be so strict in writing things. But this is what we understand by that, yes. So if you want, you can write this as 3 different conditions, but you don't need to do that. And this exists part is equivalent to saying that the limit of the left side, the left-hand limit and the right-hand limit, they are the same.
the left hand side and the right hand side become equal if there is two black dots?
No, there is, oh, okay, how can you answer this question? If I have two black dots, I don't have even a function. A function should assign one single value for each x value. If you have two black dots, and then if this is L, this is M, if I ask you what is f of A, what is the answer? L or M, so this means this is not a function. A function means you have to assign a unique value for each value. If you are assigning two values toward it, it is not a function. And it's just a relation. Yes? It's not a function. That's not the graph of a function. So everything that we work here, we are talking about functions. So you will not face this scenario. If you face, you should say this is not a function. And then the limit of functions are defined. The derivative of functions are defined. Okay, so this is the definition of continuity. Okay, so let me give you some examples. For example, let f of x be equals to x squared. Is f continuous at x equals to 1? It's a very, very simple question. I just want you to repeat the definition. So of course you already have the graph of this in your head. So what is the answer, do you think, according to the graph that you have it in your memory? It is positive, yes, because it's a continuous curve. It is continuous. By the way, it might happen that the function is continuous at one point, discontinuous at the other point. So you see that this function is discontinuous exactly at this single point, but it is continuous everywhere here before that and everywhere after that, yes? So this continuity is a local concept, yes? Okay, so you know the answer, but if you want to do it rigorously, the logic is the opposite way around. So it means that you don't have access to the function, the graph of the function. You want to predict something, a behavior about the function. So what you do, you calculate f of a first. In this case, a is 1, so you calculate f of 1, which becomes 1 to power 2, which is 1. So f of 1 is 1. And then you also calculate the limits of the function when x approaches which number? The number that you are interested in, x equals to 1. So this means that I calculate the limit of x squared when x is equal to 1, and hopefully you know that the answer is again 1. So this implies that the limit of the function when x approaches 1 and the value for the function are the same. So this means that yes, the function f is continuous at x equals to 1. But if I want to give a little bit more elaborate problem, so let me just, a little bit more complicated. So example, I can give you functions with different rules. For example, I would say that let f of x be equal to the function, for example, 2x squared plus 1 if x is greater than or equal to 1. And then I would say 5 minus 2x if x is less than 1. So this is a function does not follow one single rule. It follows two rules depending on the input value. Yes. So is f continuous at x equals to 1? Okay. So I hope that you have a good interpretation of this function. So you send x in, but depending on the value of the input, if it is greater than 1 or smaller than 1, the function applies different rules on them. Yes? So when I send x here, the function checks the input. If the input is greater than 1, it uses this rule to process that. If x that you send in is less than 1, it uses this rule to process that. And then I want to see if this function is continuous at x equals to 1 or not. So again, the first thing that I have to calculate is f of 1. So I calculate f of 1. Okay, but tell me, f of 1 is which number? Which rule should be used to calculate f of 1? Yeah?
2x to the power of 2.
This rule should be used, but use it. It means you replace x with 1. So when you say f of 1, you have to replace x with 1. But x of which rule? The first rule, because this is admitting the x equals to 1. So this means that you go and take the first rule and replace the x in the first rule by 1, and then you calculate, it is 3, so f of 1 is exactly equal to 3. Okay, the second step is to calculate limit of f of x when x goes to 1. I want to check that. And if it happens, the question mark is 3, then it means it is continuous. If the question mark is not 3 or does not exist at all, then it means that the function is not continuous. Okay, but I have a little bit of problem. Yes? Because when x goes to 1, it means it is close to 1. And it is not clear. It is close to 1 and lower than 1, or it is close to 1 or higher than 1. And unfortunately, it matters. Because the behavior of my function changes exactly at point 1. If x is greater than 1, function uses this rule to calculate things. If x is less than 1, the function uses this rule. So how can I solve this conundrum? Yeah?
You have to see if the limit from the right.
Yeah, so it means that this motivates me to look at the limits from the left and right separately. So my goal is still to answer this question mark, but instead of doing that, because of these technical reasons, for example, if I wanted to calculate this, am I in trouble? No, because x approaches 2, here is 2, and here is 1, the problem happens at this point. But when I am very close to 2, either on the right or on the left, I am still on the safe side. I am still larger than 1. So I can use only this rule. But at point 1, even if I am slightly bigger than 1, I have to use this rule. And if I am slightly lower than 1, I have to use a different rule. So that is a problem. So you see that this limit, when x goes to 2, it means that x is very close to 2. When it is very close to 2, it means that I am already on the right-hand side of 1. So I can always use this rule. Okay? So if you want to, we can write it as something in going, yes? So if I ask you to calculate the limit of f of x when x approaches 2, you would tell me that, okay, I only use the first rule, because when x is very, very infinitely close to 2, it means that definitely I am larger than 2, so I use the first rule. And then if I ask you to calculate that, okay, you put 2 here, 4, 8, 9. The answer is 9. But now, I want to know the function exactly at point 1. So this will motivate me to answer 2 questions. What is the limit of f of x when x approaches 1 from the left side? And what is the limit of f of x when x approaches 1 but from the right side? So I want you to understand that I had to break it into 2 parts here because of the nature of the function. Okay, but if I want to answer the first one, I already know which rule to use. Because when I say x approaches 1 from the left-hand side, it is guaranteed that x is less than 1. So this rule is applied for all those values. So this means that I replace f of x with which rule? The second rule. What is that? 5 minus 2x, x goes to 1 from the left. But what's the answer? Don't get confused. Minus, this is not a minus 1. This just tells me in which direction I am approaching to 1. So if x is exactly 1, this value is exactly 3. When x is close to 1, this is close to 3. So the limit is 3. And then I calculate this one. So the limit of f of x, x approaches 1 from the right-hand side. Which rule should be used? The first one. So this becomes 2x squared plus 1, and then x goes to 1 from the right side. So what's the answer? 3. And then from the equality of these two, what can I conclude about the question mark? Because the left limit was 3, the right limit was also 3, and they are equal. So my conclusion is that the limit is also 3. And then comparing these two, what can I conclude? The limit of my function is equal to value of the function. So this means that yes, f is continuous at x equals to 1. Yes? So that's also, that is at this level is enough. So you just don't need to look at the complicated functions. So for example, if I want to give you an intuition, if I ask you to draw the graph of this function, I just want you to understand the graph. So you know that this is a parabola. Yes, 2x squared plus 1 is a parabola. So here is my 1. If I put 1 here, it becomes 3. For example, here is 3. And then you know that this is your parabola. Okay? But this is the full parabola. This is not a full parabola because it is acceptable only if x is on the right-hand side of 1. So this means that you clean this part and you are only interested on this part of the graph. So you see this is 1. On the right-hand side of 1, you are following this rule. So this, if I draw that, that is a full parabola, but I am interested in this parabola if x is greater than or equal to 1. So this is why I clean the other side. And then this one is a line. 5 minus 2x is a line whose slope is minus 1, and the y-intercept is 5. Here, if you remember, it was 3, so 5 is a little bit higher. So here is 5, for example. And if I ask you to draw the graph of this function, you immediately see that the graph of this function is this line. But this is only acceptable if x is less than 1. So this graph is on the left-hand side, so I have to clean the right-hand side of it. So you see the graph is like this. So this is the graph of that function. It's a sharp point here, yes? So if I ask you the graph of that function, but you feel the graph is continuous. So, and it was confirmed with that calculation, even if we didn't know this one. So this is the graph of this function. It is one piece, and the calculation actually confirms. So these kinds of things. Okay, the next concept, as I have written the title, so we talked about limits and continuity. That's also an important concept about differentiability. So, how we can understand differentiability using the graphs? Because you remember differentiability, what is the meaning of differentiable? So let me just remind you. Because I might have a function that is not differentiable. So far, systematically, we didn't talk about differentiability. Of course, you should know a little bit about differentiability using the tangent graphs and things like that, tangent to the graphs. So I told you that a function f is differentiable at this a if the limit, do you remember that was the definition, f of a plus h minus f of a over h goes to 0 exists. Yes, that is the meaning of differentiability. So we say that f is differentiable, yes, at x equals to a if this limit exists. So that was the meaning of the function differentiable. And if this limit exists, there is a name for that. The name of that was the derivative of f at a, and because it was important, we invented a symbol for that. F prime of a. So this is the meaning of differentiability. F is differentiable at x equals to a if this limit exists. Okay, but there was a geometric interpretation of this derivative. What was that? What is the meaning of the number that you get out of this calculation? Yes?
The k value of a
The
tangent.
k value of the tangent. So it means that there's a close connection between these two. Okay, so it means that if you don't have the notion of the tangent line at some point, you are losing differentiability. Yeah, is that clear? Because if it is differentiable, it means that the value that you get is the k value. So if you do not have the notion of the tangent at some point, it means that there is no derivative at that point, and it means that the function is not differentiable like that. For example, let me just try to test your intuition. For example, do you think that this function, whatever it is, the graph of this is this one, is it differentiable at here? If I ask you this question and you want to answer this geometrically, so let me just draw this graph. What is important for me? A straight line is coming, and then a parabola is going out. If I give you a ruler and a pen, and I ask you to draw a tangent line at this sharp point, can you do that in a sensible way, intuitively? Yes, because there is no tangent line making sense there, yes? So which one is tangent? Do you think this is tangent?
Yes.
No, but why? What about this one?
Yes.
What about this one?
Yes.
So it means that it doesn't make sense because it's not a unique thing. So it's not tangent. So one idea is that, yes, this function, whatever it is not differentiable at that point because the notion of tangent line loses its sense, yes? Okay, another type of things, can you imagine? Another type of problems. For example, if I give you this graph, so one thing that you need to remember is sharp points. Okay? Can you tell me another type of points, yes?
One where we have it going like this, two lines, one going down, one going.
So like, you mean like this?
Yes.
But that's also sharp point. Yes, that's correct. But that I consider as sharp point, yes? Yes, that's correct. So if I want to categorize them, one category of non-differentiability are the points we have sharp points. But another category is?
Or there is, or the graph is continuous except where.
Exactly, discontinuous. Because if you have discontinuity, for example, if I give you the pen and the ruler and I ask you exactly, and then I give you this point, and I ask you to draw a tangent line to the graph exactly at x equals to a. You cannot draw the tangent line. You can draw half tangent lines, but they are half tangent lines. They are not tangent. Might be you can say, okay, I draw this one. But I cannot call it a tangent because it is tangent to the right side, and the other one is tangent to the left side. So it means that I do not have a tangent. So discontinuity is also problematic. So if I want to have differentiability, I shouldn't have continuity, yes? And I shouldn't have sharp points. There is another one which is not discussed in the book. It is simple, I just want to give you an information. Can you imagine another type of points which is continuous without any sharp points, but still, and the tangent exists, and still we do not have differentiability?
Is it the function of the circle?
No, that circle is not a function again. No, because if you have a complete circle,
Yes.
It is not a function. Whenever you draw a vertical line and it intersect the graph more than one point, it means that that graph is not graphable function. Okay, so can you imagine, this is not in the book, but this is extremely simple. And these are the three categories of non-differentiability points. So I want you to draw a graph which is continuous, without sharp points, having tangent lines, but is still not differentiable. Yes?
The sign is way above the cosine.
No, sine has differentiability everywhere.
So you're thinking of a straight line.
Oh, by the way, that notion of a straight line is also good to talk. A straight line, what is the tangent line to a straight line?
The same.
The same straight line. You might say that this is ridiculous to say that the line is tangent to itself, but why do you think we can feel it? That's correct. So if I draw a tangent line, if I draw a straight line and I give you this point and I ask you, okay, draw a tangent line to the line at this point, what do you draw?
The same line.
The same line. If I give you this one,
The same line.
this becomes the same line. Is it understandable? It seems that these extreme cases, you can put them as conventions. But can you justify this is a good idea? Yeah?
I mean, the tangent is defined as a function which has the same k value at
Yeah, but you are defining it mathematically.
Okay.
I just want to understand it
Well,
intuitively.
it has the same slope and it passes.
Okay, but the notion of tangent, to be honest, we don't teach this in primary school. We give circles to students and talk about the tangent to the circles, and everyone intuitively feels that. But we don't draw a line and say to the poor kids to draw a tangent line to this line, because they still don't know about the slope and they get confused. And they have right to get confused, because the feeling of tangent is something to a curve. But what I can just justify it, every straight line is also a circle. But that circle has a very huge radius. And that is why the way some people believe that this earth is flat. Because they walk on the earth and say that everything is flat, because it's a huge sphere. The radius, by the way, is 6,400 kilometers or so. But now assume that you have a circle whose radius is trillions meter. Then you really cannot differentiate the circle and the straight line, yes? And in that case, if I ask you to draw, so assume that you have a huge circle, okay, but still that's not a huge circle. But that it becomes really flat, or to any degree of precision. So if I want to draw a tangent line, it is still a tangent line to a circle, but that circle is so big that if you draw the tangent line, it becomes the same line itself. Do you understand that? Because if this is very, very big, so this deviation from straight line is so small. And if I ask you to draw the tangent line, so you just draw the tangent line like this. Okay? That's sensible. But still, my question is different. Can you draw a graph without this problem of discontinuity, without this problem of the sharp point, completely smooth, and you can also draw the tangent line, but still the function is not differentiable? Okay, so let me just draw one for you. For example, I assume that this is your vertical line. So let me just draw. I have a vertical line here, but I draw the graph like this. So I come here, and I try to make a tangent like this. And then, instead of going backwards, if I go backwards, that's not a function. I go this way. So, yes? So there is no sharp points in the black curve. There are no discontinuity in the black curve, and this is also tangent in any way humans think that's a tangent. But this function is not differentiable at this point A. Can you tell me why? So I mean that if this is function y equals to f of x, f prime of A does not exist. Why is that? Because f prime of A is supposed to give you the k value of the tangent line, yes? But the vertical line, that doesn't have any k value. It's not defined. So these are three categories of points that the function is not differentiable. So you need to remember them. Two of them is in the book and you have to remember them. One of them is the sharp points and the other one is the discontinuity. And the third one, if you're interested, are the points at which the tangent is vertical. Yes?
Is this last one like a sideways parabola?
What?
If you have a sideways parabola, is it?
No, sideways parabola again is not a function. Hussein, do you understand that? So if you have a function,
Yes.
so
And you have a
if
sideways
this side one parabola
Yes.
is not a
It's
function.
not.
No, why? Because if I draw this line, it will intersect at more than one point. A function should assign a single value to each value of x that you choose in the domain. Okay? Yes. So this is another scenario. Yes? Is that clear? Okay, so for example, that's not, by the way, if I want to give you a function, the third root of x behaves like this at the origin. So if you draw using GeoGebra that function, you will see that this function is this. And then it is not differentiable there. Okay, is that clear? So these are the three categories of points that the function is not differentiable. Okay, so differentiability is a stronger condition than continuity or the other way around. That's also important. Which one is more stronger than the other one? So if you demand that your function is differentiable, this also means the function is already continuous. Is that right? So it means differentiability implies continuity. But the other way around, do you think that if a function is continuous, you can also say it is differentiable?
No.
Why not? This one, it's continuous, not differentiable. The sharp points, it's differentiable, not continuous. So continuity and differentiability together brings so whenever you have a function which is continuous and differentiable, in mathematics they say it's a well-behaved function. So you don't have any surprises, yes? It's a smooth curve. Not only it is continuous, but you don't have troubles, yes? Because sharp points are troubles for us, so because suddenly something changes at the sharp points. So this is why we really like well-behaved functions like this. Okay, and let me just summarize everything here. And one more example, we are done. So we learned that differentiability. Let me just write it. So differentiability implies continuity. Continuity implies differentiability. We want to value them. Discontinuity implies non-differentiability. Okay, so true or false? This tells you that if a function is differentiable at a point, it guarantees you it is continuous at that point. This tells you that if a function is continuous at a point, it guarantees that the function is differentiable at that point. This tells you that if a function is discontinuous at a point, it guarantees that the function is not differentiable at that point. We want to value them true or false. So, true or false? If the function is differentiable, is it guaranteed that the function is differentiable, is continuous?
Yes.
Yes, this is guaranteed, even though rigorous proof of that is beyond the scope of this lesson. But you already know that based on what I told you, this is true. Okay, what about continuity implying differentiability?
False.
This is false, yes? When I say it is false, it means that there is at least a counterexample. And the counterexample is the sharp point or that vertical line. So that is false. But what about this one? This continuity guarantees non-differentiability. Yes, because if you have this continuous function, the notion of the tangent line doesn't make sense. So it means that, yes, this is also true. Okay, an example here is this. This is a classic example because these are just vague ideas. I try to sell them to you by drawing graphs. At this level of lesson, it's good, but that's not a rigorous mathematics because we have to prove things. And the classic example here is this. The absolute value function, yes, if you remember from the last year, the graph of the absolute function is like this. And then this function, I can draw it with one pen stroke, so it is continuous everywhere, including the origin. But is it differentiable here? It's a sharp point, so it's not differentiable. This one, you need to know it in analytic way. So we show that is continuous at x equals to 0, but not differentiable there. Yes? So this is a counterexample for this one that you told me it is false. It is an example of a function which is continuous, but it is not differentiable. It shows that this argument is false. Continuity cannot imply differentiability. But this you need to know it in an analytic way according to the book, so let me just do that, we are done. So why this is continuous? To check the continuity of this function mathematically, I need to calculate f of 0, because my point of interest is 0. It becomes absolute value of 0, but absolute value of 0 is 0. And then I calculate the limit of f of x when x goes to 0. This becomes the limit of absolute value of x goes to 0. And then what is the answer? What are the values of this getting approached? Because you know that absolute value of x is the distance of x to the origin. If x itself is getting close to the origin, the distance also getting 0. So that's also 0. So this means that the limit of f of x when x goes to 0 happens to be exactly the same as the value of the function. So this means that f is continuous at x equals to 0. Without invoking actually the graph, without seeing the graph, by analytic work, by calculating limits and things like that, we realize that yes, the function should be continuous at that point. But differentiability is a little bit subtle, so let me talk about that. So what we want to do for differentiability, I need to calculate the limit of f of a plus h minus f of a over h when h goes to 0. In this problem, I want to know the differentiability at 0. So a in this problem is 0. So what I have to do, I have to calculate this limit when a is 0. So when a is 0, it becomes f of h minus f of 0 over h goes to 0. I have to calculate this limit. If this limit exists, just calculate this one now. So, okay, so if I want to calculate this, I need to, the function is the absolute value function. So what is f of 0? I have already calculated f of 0 is 0. So forget about the second part. What is f of h? F of x is absolute value of x, so f of h is absolute value of h. So this becomes the limit of absolute value of h over h goes to 0. But then I get some problems here because I cannot simplify absolute value of h with h. Yes, they are not the same things. So I have to get rid of the absolute value sign. But the absolute value sign, I cannot get rid of it because I know that h gets close to 0. It means that it is close to 0, but it is not guaranteed if it is on the right or on the left. And if it is on the right of 0, h is positive. And if it is on the left, h is negative. And that is problematic when it comes to absolute value. So this motivates me to consider two scenarios, yes? One scenario, I consider this when h goes to 0, but from the right-hand side. And then another scenario, I consider the same limit, but when h goes to 0 from the left-hand side. If I am lucky and these limits are the same, then I can go back and say that this limit is also that number. If they are not set the same, I am still lucky because I can say this does not exist, yes? Okay, how can I calculate this? What is the absolute value of h here? H goes to 0 from the right-hand side, it means that h is positive. If h is positive, absolute value of h is equal to itself. So this becomes h over h goes to 0. But then I can simplify that, so it becomes 1. But in this case, what happens? H is negative. So what can I say for absolute value of h? Negative h. But then this simplify, but the answer is not 1, is minus. And these two does not exist. They are not the same, so I can go back and say the limit does not exist. And when the limit does not exist, therefore, f is not differentiable at x equals to 0. Okay? So I realized that I have a function. I was able to really make it rigorous. So I introduced a function. Of course, we had this intuition in mind that this is a sharp point, but this confirms that. So these things can happen when you have a sharp point. This means that when you want to calculate the limit related to the derivative, then it means that somehow you cannot answer it. You have to break it down to two pieces, and then the answers for the pieces are different. And then you can come back and say that. So this is what is happening for the sharp points. And that's exactly the reason. For example, if you have this curve and that one, it's a sharp point. Why this is not differentiable? Because the tangent line to the left side is this, the tangent line to the right side is this. And the k value and the k values are different. So if this value is k1, this is k2. Yes, they are not the same. So it means that when I look on the left-hand side, I have one slope. So it means the left limit is k1, but the right limit suddenly becomes k2, okay? So it means that if you start following this, everything goes smoothly here, but when you reach to this sharp point, you have a sudden change in the slope. Okay? Yes?
The limits coming from the left-hand side with the 0 on top of the negative side.
Yes.
Why did you put the negative sign in front?
No, because that's the definition of absolute value. Don't force me to go back to matrix C. So absolute value of a negative number is negative of itself.
Yes, but if you have absolute h, why didn't you multiply it by negative first?
No, absolute value of h when h is negative is equal to minus h. Yes? So absolute value of minus 2 is minus 2, which is 2, yes? And that's the definition of absolute value. And then last year we talked a lot actually about absolute values. So you have forgotten, you can go and review some of those videos from last year. Okay, any questions? Okay, so I'll stop here, but this I need to talk a little bit. By the way, that one we also studied, the limits when x goes to infinity is another part of this lesson, but we will come back to that later. Any questions? Thank you.